Hello Math 4411 students, let's begin Lesson 2, Groups. But before starting, let's have some discussions on preliminaries. In particular, I'd like to talk about equivalence relation and modular equivalence as an example of that. The modular equivalence will be useful in section 2 of this notebook, so remember that, and let's begin. Here's the definition of the equivalence relation. A relation on a non-empty set is called an equivalence relation if it is reflexive, symmetric, and transitive. Remember all that? If you have an equivalence relation, then you can define equivalence class. Starting from a certain set, a non-empty set X, which you can regard as a universal set because everything takes place in this set, almost everything, and this is a superset for almost everything we are going to consider now. And starting from a certain element A from that set capital X. And then we define the equivalent class of A as a subset of capital X like this. The set of all elements of capital X that are related to A. And this is called the equivalent class of A, and the first element A is called a representative of this class. Please note that I use the term the equivalence class and a representative. That's because there's only one and only one equivalent class for a given element, but each equivalent class can have multiple representatives. In this set, all the elements here qualify as a representative. So unless this set is a singleton, it can have multiple representatives. Typically, we use this bracket notation to represent an equivalent class and representative, but sometimes we use a bar notation. This is typically the case when the starting set is an integer, the set of integer. In that case, we typically use bar, but not always. For now, let's go back to bracket notation. Let's stick to the general case here, at least for the time being. Now, here are some properties of equivalent classes. First, observe this. And do you see why? Oh, I was a bit premature closing this. Remember this property, reflexivity? A is related to itself. Therefore, something is not right. Okay, all right. I got the correct font now. Okay, all right. Where was I? By the reflexivity, A is related to A, therefore it satisfies this condition. Consequently, A belongs to the equivalence class A. And this holds for all elements of X, so we can rewrite it as kind of like this. For all elements, A is related to its own class. You can use other characters too if you want to. Doesn't matter. Okay, that was related to reflexivity, but there are other properties too, symmetry, and the trickiest, the transitivity. Now, how do they translate to other expressions here? Well, here we go. If A and B are related, then the equivalence class A and equivalence class B are the same. Now, if they are not related, then the classes are not only different, but also disjoint. Interesting, isn't it? Equivalent classes are either identical or disjoint. Black or white, no gray. Let's come back and prove those, but for the time being, let's accept these two properties and let's go to the third property. If we just take the union of all, then clearly that's going to cover entire capital X, like this. You see? Reflexivity gave us this. For every element, X belongs to that class of X, bracket X. And consequently, if I just take the union of them all, then certainly I'm going to cover entire capital X. So they're the same. The left-hand side is superset of everything, and the right-hand side covers even that, so they're the same. But then again, this union is really, really inefficient because there's so many duplicates. There's so many equivalent classes that are identical, counted twice, thrice, infinitely many times, whatever. So trim those out and choose one, and then throw all the others away, and rearrange all these as x1, x2, x3, and so on and so forth. And that could go on forever as an infinite set, if needs be. Then that union becomes a disjoint union thanks to the second property here. You see, there's so many duplicates, so we throw all those away and choose one for each, so that we get unions of different equivalent classes, but different means disjoint. So we end up with a disjoint union. This we call an equivalent partition. So equivalence class automatically generate equivalence partition. Now let's come back and prove these. First property and second property, they are both biconditional, so we have to prove both ways. Their structures are kind of like these. One direction, the other direction. One direction, the other direction. Let's consider the first case. Assume A and B are related, and we have to prove these two sets are the same. What do you mean by that? Two sets are the same. Elements here are elements there, and vice versa. So elements of A, if and only if elements of B. That's what you have to prove. Basically this. If X belongs to bracket A, then X belongs to bracket B, and vice versa. X belong here if and only if X belong there. But then again, what do you mean by X belongs to the bracket A? X is related to A. You see, that's a condition. And X belongs to this bracket B means X is related to B. Now are these two equivalent, as I highlighted in this red? The answer is yes, because of the transitivity. You see, A and B are related, and X and A are related. Then X and B are related, transitivity. And vice versa too. X and B are related, and A and B are related, then X and A are related, transitivity and symmetry, if you will. How about the other direction? Assume these two are the same, and then we have to prove that A and B are related. Actually, that proof is actually even easier. A belongs to bracket A, of course, but then again, that's bracket B by assumption, and consequently, A is related to B. The detail is left to the students. Now, how about the other one? Well, this forward direction is going to be the trickiest. Assume that A and B are not related, and we have to prove this is an empty set. So how do you prove something is an empty set? Well, let's choose something from the intersection as if this is non-empty, and let's drive a contradiction. Select X from the intersection, so it belongs to A, and also it belongs to B. But then again, if you use the transitivity, X is related to A and X is related to B, then A and B are related. But that's a contradiction, you see. We started with A and B not related. So what's the conclusion? This can't happen, so there's no such X. We have an empty set. I think that's the trickiest of all. The other direction is not too bad. If you take a first step, it's not too bad. We assume this. Let's assume A and B are related. And then use the same thing that we did before. Consequently, A and B are the same. Bracket A and bracket B are the same, and thus the intersection is non-empty. Okay, that proves everything. So we have this special set of properties for equivalent classes. Equivalent classes are either identical or disjoint. So if I union them all, then dropping all those duplicates, we get a partition, which we call an equivalent partition. And now, if we define another set like this, the set of all equivalent classes, as the quotient set, and it's well defined because you see we have the starting set, the power set of X. You see all these, this one here, that's a subset of X, or it belongs to the power set of X. So this is well defined. And we define a quotient set like this. Now the quotient set gives me, roughly speaking, the number of classes. And then number of each classes, if you multiply them, you're going to get the cardinality of X, so to speak. And that's only for finitely many cases, of course. But even if you increase this idea into infinite sets, you can still deduce somewhat similar argument. The quotient set can have smaller cardinality compared with the original. Not always, but sometimes they do. In other words, each of these can be humongous, but the number of equivalence classes can be small. Please remember that because we're going to use that in this example, modular equivalence. Okay, so much for equivalence class, equivalence partition and quotient set, everything. We have some time left, so let's take care of some basics here. This is how we define equivalence relation, yes. But as a matter of fact, please recall that everything came from Cartesian product. And we defined a relation as a non-empty subset of a Cartesian product. Examples include a function, an equivalence relation, and an order relation. And in this expression, everything is represented in terms of pairs and set membership because we can all point toward the Cartesian product as a matter of fact. So X is related to X can be rewritten as X comma X belongs to this relation. And X is related to Y can be rewritten X comma Y belongs to this relation, and so on and so forth. And of course, more traditional version is like this for equivalence relation. And you can do the same thing for other expressions as well. But the order relation is not that important for our purpose. It's important in analysis, but for algebra it is not, so let's not worry about it. And as for the function, that's a bit too elementary. So equivalence relation, which can be written like that in terms of Cartesian product and pair notation versus this traditional notation, they're identical. And as for the precise definition of the Cartesian product, if you're interested, you can define like this. Ordered pair can be defined like that, and Cartesian products can be defined like this with the starting set.